Hi everyone, welcome to February 2026 Galaxy SIG seminar. I'm your host, Aaron Young. Benny is off to give his own colloquium elsewhere, so he might be able to join us later, but I'll be running the show today. So today we have John Weaver coming to talk to us from MIT. And instead of doing the boring auditorium style introduction, I'm actually going to ask John to introduce himself. So John, very briefly, tell us about your origin story. How did you get involved in astronomy? Where have you been and where are you now?
Yeah, sure. So, hi everyone. My name is John Weaver, and thank you, Aaron, for the invitation, and thank you for SIG for reaching out. So, I got my start in astronomy actually through a local planetarium that was installed to teach the U.S. Coast Guard cadets how to do celestial navigation. So, I started there as a young assistant to the planetarium lecturer when I was a teenager. And that and listening to Carl Sagan's Cosmos, I fell in love with it. And I've been doing astronomy ever since. I knew I wanted to do this since I was in high school, and actually a lot of my first astronomy classes were here at MIT. So it's amazing for me personally to have that whole thing come full circle and be in a place that helped contribute to my career trajectory. Since then, I did my undergraduate studies at the University of St. Andrews in Scotland, even though I'm originally from the Northeast in the US. And then after that, I was at the brand new Cosmic Dawn Center, then brand new in 2018, at the University of Copenhagen as the first round of PhD students there. After getting my PhD in 2022, I was a postdoc with Kate Whitaker at the University of Massachusetts Amherst. And then since the fall of last year, I've now been a Brinson Prize Fellow here at MIT's Kavli Institute.
Great. That's an introduction I cannot give, so thank you for doing that. So just one more question. Have you always been working with galaxies? When did you discover galaxies?
Yeah, so yes, the answer is yes. And there's not really a complicated story about it. The first project I did was as an NSF REU student working on a very UV luminous galaxy falling into Fornax, NGC 1427A. You never forget these things. And from there on else, I was just studying galaxies, galaxy mergers, post-starburst galaxies. And then in graduate school, I got into higher redshifts. And now I've spanned everything from such low redshift you don't account for it to now needing to do the complex cosmology and caring about these things. So it's been quite the journey, but it's been a lot of fun.
Awesome. All right. I look forward to hearing your talk and what have you currently been working on. So John's going to tell us about monsters in the dark, unveiling the nature of ultra-luminous galaxies at cosmic dawn. So John, take it away.
Yeah, thanks, Aaron. Right, so I'm hopefully going to take about half an hour to talk through this. And I think it'll probably work easiest if we reserve questions for the end, because I have a couple of prompts and things that we can discuss on sort of the last slide. So we'll just get started. Before we jump into high redshift galaxies and galaxy formation, I, as somebody who really enjoys history, want to contextualize all this a little bit. So we've known for only about 100 years about the existence of these island universes, which of course we now call galaxies outside of our own Milky Way. It's been a remarkable 100 years, how much we've progressed since Hubble's landmark discovery. But I think almost immediately after finding this out, we sort of realized that there's different classes of galaxies, and this is Hubble's tuning fork. And we've gone from there to understand the myriad interlinking physical processes that explain that tuning fork, now being more comfortable with terms like red dead ellipticals and star-forming spirals. And we understand the reasons surrounding why we have that very rich bimodality in the present-day universe. And I think much of what we're interested in studying galaxy evolution going back to the Big Bang is to understand where that bimodality came from. And for me, it's a story that is a lot about density and a lot about the overdensity of galaxies and how that relates to dark matter and how we can use the overdensity of galaxies as a cosmological probe and the massive galaxies within them. And so the Perseus cluster is a perfect example of this image being taken by the Euclid telescope about 2 years ago now. And it sort of summarizes everything that I want to talk about for massive galaxies in the local universe. So we see these red, dead elliptical galaxies that are no longer forming stars. They are spherical, oblate. They don't have that coherent disk shape. They're rotation dominated. They don't have coherent velocity motion like we have in spiral galaxies. And they tend to live in clustered environments. And all this together tells a story dictated primarily by gravity about how these galaxies spawned in the early universe, formed together, and went through how I'd like to call it accelerated galaxy evolution, right? So galaxies in the field are going to progress more slowly because they have less access to gas, because they're not in a gas-rich, overdense part of the cosmic web. But galaxies that formed out of the nodes in the cosmic web have that access to gas, formed their galaxies early, and had accelerated tracks of galaxy evolution. So the way I like to think about it is that by studying massive galaxies across cosmic time, you are looking at an accelerated clock, a laboratory that allows you to see how things progress in accelerated galaxy evolution, which naturally is also the most extreme. And by being most extreme, it provides critical constraints on our best theories of galaxy evolution. And those themes that I just highlighted are sort of what's going to set the stage for the rest of the talk. So now coming from a theoretical point of view, where we can observe things or see things that we can't directly observe in the universe, I wanted to highlight a beautiful video from the Lustrous TNG simulation showing the formation of a massive galaxy cluster and how it relates to the cosmic web. And I don't think any observational data set can do this quite as well as the simulation can. All right, so here we see the formation of nodes in the cosmic web. They're giving rise to the most massive galaxies fueled by the largest reservoirs of cold molecular gas available in the universe. And under the action of gravity, they are collecting their neighboring satellite galaxies, growing through mergers, and also growing through in situ star formation. Ultimately, as time progresses, different nodes begin to find each other and merge as these collections of galaxy clusters that come together to make the most massive galaxies we've ever observed in the universe. And I think this is a very compelling story. I think it's a very compelling narrative. And so massive galaxies are related to the location of dark matter overdensities. Without the overdensity of dark matter, we typically wouldn't expect to find a massive galaxy. These massive galaxies, when you find one, you typically find many. They seem to live in galaxy clusters because the conditions are ripe in these dark matter overdensities to form many massive galaxies in one local environment. And then, as I said, that these locations in the cosmic web, these very privileged locations of the cosmic web, are where we would see this rapid evolution, where galaxies seem to have grown up very quickly and stopped their star formation relative to the abundant blue star-forming spirals that we see dominate field environments where we don't see that density. Now, thankfully, we don't have to be content with looking at the local universe to try to piece together this picture. In the words of Carl Sagan, the universe is a time machine, right? So because the finite speed of light, we can look, the further we look back into the universe, the further we look back in time. And so by looking at some of the most distant galaxies, we are also looking at some of the earliest galaxies. And I know this is a philosophy well known to folks at Space Telescope. And this fly-through, of course, wouldn't be possible without the groundbreaking work of the Hubble Space Telescope. And so the point here is to take what we know about the local universe and to go back in time to understand their origins and how this rich bimodality came together through the lens of massive galaxies as laboratories for accelerated galaxy evolution. Within that context, I think one of the greatest and most surprising successes of the Hubble mission was the discovery of GNZ11. This is a very luminous red galaxy within the Goods North field, one of the Candles fields, confirmed at a redshift of 11. I guess now it's 10 point something thanks to a follow-up from James Webb. But this was remarkable. Within the Goods North field, no model predicted we should have a galaxy this luminous. And so just by itself, the existence of GNZ11 within the small area of Goods North provides exceptional statistical leverage on our greatest theoretical models as to how a galaxy should be forming. So this was really a mystery that I think many of us were anticipating Webb would resolve either by showing the galaxy to somehow not be at redshift 11, or understand that it has some extreme physics, something like that. And that's, I think, the story we've been seeing over the past 5 years that I want to take a moment to talk about. So there goes James Webb. And almost within the first few days of the data release in that fateful summer, Webb smashed that redshift record. And so I'm showing here two cutouts from the Abell 2744 glass early release science field, where Rohan Naidu, myself, and others discovered these two exceptionally luminous, exceptionally high redshift galaxies, one of which was a photometric redshift of 12.5, which was then subsequently confirmed, thus becoming the highest redshift galaxy in the opening, I would say, hours of the Webb mission. I think that was also very, very, very exciting. And just like GNZ11, these galaxies are far too luminous for the volume of the universe where they reside in. And that's, again, confirming that these theoretical pictures are either incomplete or we need to tune something there. And more recently, Webb has broken its own record again, finding a galaxy at redshift 14.3 from the JADES collaboration. And this time in Good South. And what's, I think, an important context to realize is it took a little while for the JADES team to find this galaxy because it was hidden behind a blue foreground galaxy. And so that highlights the importance of being able to deblend your galaxy catalogs. And as somebody deeply interested in making catalogs, that's a dilemma or a thing you need to pay attention to that's very near and dear to what I do. And so I think this galaxy here at 14.3 really highlights how we need to be very careful when we go and make galaxy catalogs, or we can end up missing some of the most exciting discoveries. And that is a theme we'll come back to later in the talk. Now, the current record holder is a smidge bit higher redshift at redshift 14.4, again, found by Rohan Naidu, myself, and others. Really exceptional galaxy, although you'll note just from NIRSpec alone, there's not a whole lot you can do. It's still hard work to try to understand the interstellar medium of this galaxy from the limited information we have at redshift 14.4, really pushing Webb to its uttermost limits. But I think this is also a very exciting and spectacular find that highlights the importance of the James Webb mission. Now, although it's very exciting to find these exceptionally high redshift galaxies, they are few and far between. And although they may be spectacular, the power of Webb is in expanding the number of galaxies we have at these high redshifts in these formative epochs deep within the epoch of reionization, where we don't have to be content anymore with one galaxy at redshift 11, but can begin to do population demographics from a statistically robust standpoint. And so here is a plot of the number density of galaxies as a function of their absolute UV magnitude. The the previous measured UV luminosity function fits are shown there in the grayscale at redshift 5 through 8 in descent, going lower in number density. And then the points here are from high redshift galaxy candidates from the SEERS and NG Deep surveys, which are sitting higher than the extrapolated redshift 11 UV luminosity function, considering the previous measurements at lower redshifts. And this was a big surprise because now we don't have just one galaxy that's above this relationship in a difficult to calibrate volume, but instead we have many galaxies forming a UV luminosity function measurement where we can begin to really examine why we see this disagreement with expectation versus the measurements on the sky. Going a little bit further to compare with theory, this is also in excess of theory. So here we're looking at that similar picture from a slightly different angle. Here, instead of the number density, we're looking at the surface density at greater than a certain redshift, and so cumulative surface density as a function of redshift, so we can see the whole redshift range, right, going out from 9 to 14 or so. And at the top, we see the positions of the redshifts of all the galaxy photometric candidates at these redshifts. And if they're all truly genuine, it would present a surface density which is not predicted by most theoretical simulations. The notable exceptions here being Baruzzi et al., which is a semi-empirical model that incorporates real observations as well. So this was the dilemma that I think emerged out of the first few months of James Webb that provided a very strong contrast to previous expectations, both from observations and extrapolating observations and from theoretical predictions. And that was very exciting. It gives us something to do. It would have been a very mundane past 5 years if everything had magically fallen into line and we would have learned nothing. Now, since that mystery began to unravel and the tension began to grow, there's been a number, and this is by no means exhaustive here, a number of proposals as to how we can change our picture of how galaxies formed in the early universe to accommodate the exceptional higher number density of these luminous galaxies in the early universe. I think the one that's probably gotten the most traction, most attention is this ultra-efficient star formation, where essentially galaxies are just happier to form stars in their dark matter halos than we expect. So something about feedback is not as strong as we anticipated, and maybe the entire gas cloud is able to convert into stars somehow. I think the physics here is a little bit tough to grapple with, but it's certainly been a knob that's been tuned by simulators and have shown to meet that agreement. I don't know personally if this is the most compelling proposal, because I think there's a lot of physics that is difficult to explain, but it's certainly one that is obvious and worth discussing and exploring. In the middle panel here is an alternative for stochastic starbursts, where the elevation in the UV luminosity function is a transient feature for an individual galaxy, but overall that galaxy is not going to contribute to that excess. And another way to think about that is the galaxies are undergoing stochastic starbursts. For a moment, they're visible, they contribute to the excess, and then they go away again, right? And this is where a galaxy is outgrowing the expected growth rate based on its dark matter halo for a very short amount of time. But because that's an observational bias, it shows up in aggregate statistics as an excess. And then lastly, but certainly not, again, exhaustive, is a model where we have this outflowing material that clears gas and dust, which then allows the starlight to escape more readily along these preferential sight lines around these cocoons of stars, which then contribute to a higher perceived UV luminosity that we observe escaping the galaxy. Now, everything that we've been talking about here is coming essentially from the candles fields. These are small, to me at least, small-ish fields that have been exceptionally powerful for informing galaxy evolution, but ultimately look at very small portions of our universe. And although they've been followed up, or they were created during Hubble and followed up by James Webb, and exceptionally notable fields, their ability to statistically constrain galaxy formation models is limited just because of their size, right? You don't know if you're looking at an overdensity or not. However, there's an alternative of the Cosmos field, which actually hosts an entire candles field inside of it, which was proposed to solve exactly that. Although it's not multiple fields, multiple independent fields, the size of Cosmos being about 2 square degrees, bigger than the full moon, we expect to be able to probe multiple or different environments, so the whole range of galaxy environments, from the most overdense clusters down to the biggest voids, in a way where we can get at with the rarest systems, so the most massive galaxies. And statistically, that equates to a less biased view of our universe. And so I spent a lot of my career working in the Cosmos field. As many of you may be aware, we put out the Cosmos 2020 catalog just shy of the launch of James Webb, which really kind of wrung the towel in terms of getting all this amazing science out before Webb launched, which is a community catalog of 2 million galaxies selected from the VISTA dataset, which is one of the longest surveys from ESO, using the VISTA telescope down in Chile. And with it, we were able to make a catalog, near-infrared selected, so stellar mass selected. And that includes Spitzer data, some of the deepest Spitzer data over 2 square degrees. And in order to get at the galaxy stellar masses, we need to treat that IRAC data responsibly. And by that, I mean we have to deblend it all. So using the near-infrared priors, we use Sursic model fitting to deblend 2 million galaxies in IRAC, where they basically all overlap each other if you consider the very long wings. And using that, developed a picture of galaxy formation and a community catalog. But I'm not here to talk about mass functions, although you're welcome to ask me about them. I'm here to talk about UV luminosity functions. And so on the right-hand side is the UV luminosity function of Cosmos 2020 at redshift 9 from Olivier Kaufmann, Olivier Aubert, and myself, where we're able to probe the very luminous end of the UV luminosity function at MUV minus 24, 23, 22-ish, where those red points are. And this is a realm of multi-degree surveys where we can go down to rarities, where you can't, rarity per volume, that you can't probe from narrower deep fields from HST and James Webb. And so these two sort of surveys are perfectly complementary because although the wider fields are shallower, we're looking intrinsically at rare but very luminous galaxies that we can still observe. We just will miss them in the smaller, narrow fields. And so together we had this emerging picture of the UV luminosity function at redshift 9, which also had an excess. In other words, this whole flurry of mystery as to the excess of luminous galaxies in the early universe, I would say we actually knew about before the launch of Webb, or at least it was hinted at. And we began to unravel that mystery of luminous galaxies at redshift 7, 8, and 9 just around the time that Webb launched. And I think both pictures or both mysteries are extremely complementary and are essentially getting at the same thing. And that's worth a moment of study. So the 5 galaxies that I show here in red, the 5 brightest ones, we went after with James Webb's integral field spectrograph, and we were very pleased to get 14 hours in cycle 1 to do this. And so we were sort of test rats for lab rats for NIRSpec, which was wonderful, and we're still working on the data. And I'm going to talk a little bit about that. So we observed 5 redshift. We thought redshift 9. Turns out they're redshift 7 or 8. I'm not going to have time to talk about the reason why. We got the data down. We had to wait a little while because Cosmos Webb was being observed and we couldn't, we were competing for that time. So it took a little while. So formally, these were observed in cycle 2. We got the data down and realized we had an enormous challenge in front of us. These were some of the deepest observations taken at the time of high redshift targets from James Webb. And so we started the task in earnest. We had to develop our own background models to make sure we got the absolute best calibration and background subtraction. We were able to get a very clean residual. So the standard pipeline at the time, which has been enormously improved, produced what we show here on the top, and our reduction is able to remove a whole lot of these things. I'll just mention, because this is a very calibration and technical aware audience, that we are feeding back what we're doing. We're going to make the pipeline fully public. And importantly, we have decided not to project the cube into SkyFrame. So we've projected into the detector frame to minimize correlated noise. And we've also tweaked the parameters so that when we drizzle everything together, we drizzle it to a higher resolution of 0.05 arc seconds per pixel, which has been enormously important for actually understanding the morphology of these objects. So all of these improvements will be detailed in our reduction paper led by one of my grad students, Negin Nazad, at the University of California, Riverside, which should be out in the next few weeks. So although we targeted 5 of them, 2 turned out to be low redshift interlopers, and I'm going to choose not to talk about that right now. Instead, I'm going to talk about the 3 high redshift galaxies we did confirm. They're shown here, redshift 7.2, 7.7, 8.2. The main reason we got the redshift wrong is the assumption of Lyman alpha. As it turns out, none of them have bright Lyman alpha, and that made the photometric redshifts overestimated. However, you see that there's an enormous diversity in these galaxies that were selected to be essentially identical photometrically, right? So we see that we have multiple components. This green guy up here is actually an interloper, I think at redshift 1 or something like that. This is the main target down here. the data is phenomenal. So here we're looking at the redshift 7.7 galaxy that we've sort of dedicated the most time to. And we notice that it's not just one big galaxy, it's at least three components. And if you take it as one large disk, you get a several kiloparsec large disk at redshift 7.7 that I really struggle to comprehend from a cosmological standpoint. And I would argue that instead we're seeing the merger between three marginally resolved galaxies. If you take their spectrum together, you get the one shown here on the right. You can see that we have some very strong emission lines, strong UV continuum, and that those features vary across the galaxy. And we're sort of seeing that the cube at different wavelength slices as we travel through the cube on the left-hand side. Now, we were not content with taking one big aperture and extracting the whole thing. We wanted to get at the individual components, and we very quickly realized we can't just do apertures in the components either. That's not going to be accurate. So instead, we have forward modeled Sirsic profiles convolving with the PSF at each wavelength slice to produce a fully forward modeled data cube model where the normalization on each component yields an independent deblended spectrum. One of my other students at UC California Riverside, Faiza Manesh, has been examining the individual spectra of the three components to study the diversity of the assembly histories of those individual components, finding that one of them potentially actually is a post-starburst galaxy with very low ongoing star formation. That's that northern component there. But overall, their growth histories are very different, which leads us to believe, indeed, that these are probably galaxies merging, and that we may even be beginning to see evidence of the first merger-induced mini-quenching episode happening there in the top component. So stay tuned. This is in prep work that we hope to have out in the next few months. As I mentioned at the start, we were really surprised at how diverse the morphologies were, and I want to really highlight that this is something we could not have seen from the ground, not even close. People have tried to take VISTA morphologies. As we've now learned, they are just not accurate at all. And so here I'm showing the cutouts from the ground-based VISTA near-infrared images at roughly the same wavelengths as the IFU cubes here shown on the bottom. And you can see the morphologies are nothing alike. The green square is the same size as the IFU cubes, and that central circle is highlighting sort of the innermost region of the object. And so it goes to show that this morphology is very surprising and definitely not what we expected from the ground-based data. And so this brings on another point. Could it be that some of these exceptionally luminous galaxies that seemingly are more abundant than we expect, could it be that they're actually unresolved mergers? By that I mean, if we separate them out into their individual component galaxies, they would be more abundant, but each one being less luminous. And because we have magnitude versus number count or number density in a UV luminosity function that actually works disproportionately in magnitude, thanks to 2.5 log 10, to resolve the tension. And I'll talk about that as we go through. I want to highlight another galaxy that we found this very similar multiplicity in. This is a galaxy in the Uncover field, again, Abell 2744, which is a beautiful lensing field studied by HFF and so on. And we found this remarkably bright galaxy at redshift 8.51 with a moderate magnification of 1.4. And like galaxies like GNZ11, the redshift 14.4 galaxy, the MOM galaxy, even though this galaxy is at redshift 8.5, it's also unexpectedly luminous for the volume in which we find it. It has an MUV of minus 21.4. It is spectroscopically confirmed. The spectrum is shown here on the right. This is 2.7 hours of observations. It's beautiful with NIRSpec. And what we noticed very quickly is that this galaxy, even though we didn't realize when we targeted it was two components, it is two components. And if you didn't have that 1.4 magnification, you never would have been able to separate them. But thankfully, serendipitously, we caught them within the same MSA shutter. Micro shutter. And so I developed an optimal extraction thanks to the pioneering work of Keith Horn in 1986 with this optimal extraction. As it turns out, that paper does tell you how to do multiple extractions at the same time. And so I used that, developed it to extract both components out of a single MSA shutter. and a single MSA trace. That requires a lot of calibration. I definitely don't have time to go into, but the result is that these two components have very different UV properties, starkly different. They're shown here in blue and yellow. One of them has Lyman alpha, the other one doesn't. That's an enormous difference in terms of the consequence for the geometry of how the Lyman alpha is escaping in these potentially two galaxies, not two components. By consequence, we have two different inferred UV spectral slopes, which correlates, we believe, with the Lyman continuum escape. If you took the galaxy as a single object, you would get that black point there that's sort of nominally on the curve for redshift 8 galaxies. But if you take the two components separately, it actually straddles the curve entirely, highlighting the variance inherent in these relationships. And that, looking at averages is not a meaningful way to actually make progress and understand the evolution of high redshift galaxies. I also want to highlight, relevant to one of those three scenarios that I showed earlier, that this galaxy also very likely is undergoing its formative burst right now. At least that's what the star formation histories tell us. And so because these bursts are short-lived but easily observed, we are catching this galaxy preferentially because it's just turning on most of its stars right now. But actually, if we caught it at redshift 9, redshift 10, it would have been UV faint and not even visible in any of the JADE surveys. All right, so we're just catching it now, which contributes, in addition to the multiplicity, to the perceived overabundance and difficult reconciling this with cosmological expectations. And so if we look on the right-hand side, I'm not going to talk about the left-hand side very much, but the right-hand side, we're looking at the UV luminosity function. If you took this galaxy as a single object, of which there is none brighter in Abell 2744, it sits well above the expected redshift 8.5 UV luminosity function. However, if you break it into two components, you reconcile that difference, and then it comfortably sits at 1 sigma. So what I'm getting at is that multiplicity in these early galaxies is extremely important. And unfortunately, without magnification, oftentimes you are not able to identify multiplicity in these objects. And to highlight the magnitude of this effect in aggregate, I'm making a straw man case here, admittedly, where we're looking at the UV luminosity function from presumably unresolved galaxies where we don't really see the pairs, and then a situation where we'd be able to resolve all the pairs. This is not based on observation. This is taking basically, if the brighter you are, the more likely you are to be pairs. And comparing those predictions or expectations in just a mocked up Monte Carlo simulation for a Schechter function UV luminosity function. And then on the right is if you had this excess UV luminosity function, which we call a double power law. Now with 0.1 square degrees, you'd really struggle to be able to tell the difference in aggregate between these scenarios. However, if we go up to 1 square degree, the difference begins to show thanks to having just more objects and beating down that shot noise. You're also, by going to larger volumes, able to access rarer populations and complete that curve going out to the luminous end. And that is where the bright end UVLF versus the Schechter function can be separated at high confidence. And that's unfortunately not a region where you can study that with deep, narrow fields. And so this is all highlighting Roman, of course, with its beautiful resolution and also wide field area, which will clean up a lot of this work overnight. And I'm really looking forward to that. And before we open up the floor to talk about Roman, I want to make a pitch for Euclid, which is doing a similar kind of task right now on the sky. And I will go to show how combining the two is actually going to be transformative for galaxy evolution science. So briefly, Euclid has two instruments. The NIRSpec instrument, which was responsible for near-infrared spectroscopy and photometry in YJH filters, and the VIS instrument, which is roughly a single wide band pass comprising classical RI and Z filters. Notably, VIS is much higher resolution. It is suitable for weak lensing. That's what it's built for. And NIRSpec is designed to give us the near-infrared leverage for photometric redshift calibrations. And so the goal of Euclid is to map dark matter large-scale structure up to redshift 2 from weak lensing signal from about 1.5 billion galaxies, and then spectroscopic clustering from about 35 million galaxies. Euclid's first observations were taken in 2024. I was very lucky to be part of some of the first science drop. And here we have a beautiful observation of the A bell, and the zoom window's in the way, 2390, highlighting Euclid's transformative field of view, which compared to Webb's field of view is just remarkably larger, right? It's many times larger the size of the full moon. And so here we're looking at basically half a square degree to 0.7 square degrees roughly when you start to mosaic and fill the chip gaps. Now, although this observation was aimed at looking at this galaxy cluster, as it turns out, you can actually use Euclid to then go and look at all the stuff around it where you don't have a ton of magnification and access an area that's effectively cosmos sized. And so that's what we did. We looked for ultra bright galaxies that are not there in the visible instrument, but are there in the near infrared instrument. So here you can see that there's dots. They're very low resolution. NIRSpec is not a high resolution instrument, but VIS is exceptionally deep and exceptionally highly resolved. And so it's a machine for finding these kind of galaxies. To show that a little bit more, here on the right, I'm showing a Lyman alpha emitter at different redshifts, then YJH filters from Euclid, which are redder and broader than classical YJH, and then this IE VIS in broad passband, which is always, thanks to our standard observing sequence, 2 magnitudes deeper than the Y band, which makes for exceptionally strong Lyman break signatures and Balmer breaks and all that kind of stuff. And so that was just a preview as to what Euclid's going to be able to do. We are on Sky. We are observing the nominal wide survey, 15,000 square degrees over the 6-year mission, down to YJH 24th magnitude, and also the deep survey across roughly 50 square degrees of 3 wide deep fields and a couple calibration fields, including Cosmos, down to YJH of about 26. Here's the location of those deep fields and auxiliary fields. And just to highlight the magnitude of these observations, I know this is probably not a surprise to Roman folks in the audience, but this is a lot of data. And it will transform our view of galaxy evolution science. And so what you see there is just a zoom out of only a fifth of the Euclid deep fields. It's incredible, but it's also an incredible challenge, and one that I know is being mounted by Space Telescope in preparation for Roman. And I think Euclid is already highlighting some of the anticipated challenges in terms of not just data download and data processing, but also educating the community that the old techniques of opening up a thing in a FITS file, opening up an image in a FITS viewer is not going to fly. And that we're going to need to, just like SDSS folks, tackle this through queries and have trust that the data products being produced in mass by these teams are well documented, accurate, and what you need to be able to do and well communicated. So what we're putting together is the Cosmic Dawn survey, taking the Euclid deep fields, complementing them with deep Subaru, hypersuprime cam, CFHT, Spitzer, 6,000 hours of Spitzer. This is about a year of Spitzer time, an enormous part of Spitzer's legacy from Euclid. And Keck. And we hope to, as I was saying earlier, probe down to rarer populations, kind of that dawn volume there compared to HST for UV luminosity functions. Same thing with mass functions. And we actually have some observations pre-Euclid just based on the Spitzer and hypersuprime cam data over about 15 square degrees, showing that we see a departure in the stellar mass function compared to expectation. And that's that darker filled curve compared to the observations there as the solid points, which point to higher star formation efficiencies for redshift 5-ish galaxies here, 4, 5, 6, which is, again, a collaboration on this UV luminosity function mystery, that the excess of ultra-bright galaxies is also a mystery that is manifest for, I think, the same underlying reasons in mass functions. We're seeing the excess there too, but you can only see it if you probe large volumes. And so again, Roman's going to be an absolute groundbreaking instrument for getting at this and cleaning it up. So Euclid's Quick Release 1 is out. The DR1 is going to be out hopefully in October of this year. And before we break for questions and discussion, I just want to highlight some Euclid-Roman synergy here. So as I think I've been mentioning, both missions offer incredible statistical leverage. They're similar in concept and design, but of course very different in terms of the resolution of near-infrared for Roman, depth, efficiency, and so on. And so both missions will offer the incredible statistical leverage on the rarer systems. And as I've been going on this whole time, they're going to complement our view from HST and JWST by finding these rare objects, these rare environments, where we really begin to push on theoretical expectations and models. There's also an incredible overlap in deep fields. Thank you to the Core Community Survey definition folks for seeing the vision and for combining Euclid and Roman, because the Euclid deep field Fornax 10 square degrees will be observed in the high latitude wide area survey, and EDFS will be completed with Roman data in the high latitude time domain survey. Thank you, thank you, thank you, thank you. You are going to set up an amazing data set. The filters are different between Y, J, and H. Roman Y is not Euclid Y. And I show that on the right-hand side here, where the filter transmission curves in the dashed lines are Euclid Y, J, and H, and the filter curves in the solid curves are solid. For those of you used to working from near infrared from the ground, you'll notice there aren't any gaps. That's amazing. We can now just do top hats. It's fantastic not having the atmosphere. But the interaction and overlap between these filters will create pseudo-medium bands, which means we get unbiased emission line detections at different redshift slices, mean unbiased emission line luminosity functions for O3 H alpha going out to like redshift 4. It's going to be incredible. As well, and as demonstrated at a recent paper from the Euclid Consortium and Rohan Varadaraj, the combination of these different filters, such as, for example, Vista and Euclid, can identify brown dwarfs with great efficiency photometrically because they are sensitive to the absorption troughs, the molecular absorption troughs in brown dwarf atmospheres, which is incredibly important for high redshift science to eliminate brown dwarfs. As well, the Roman resolution is critical for deblending NIRSpec and will be a wonderful prior for detecting on Roman, developing our galaxy models on Roman, and then deblending NIRSpec and also IRAC. And if we can get some K-band data for Roman, that would be amazing because it would bridge that gap with IRAC and make those priors that much more powerful. And Roman also offers, especially for my science and the dilemma that I proposed here with the multiplicity, offers kiloparsec level pair identification at redshift 8 versus about 4 kiloparsecs for NIRSpec. And I highlight there the magnitude of our issue, our dilemma here in the top right, where although James Webb NIRCam is able to blend these galaxies, it's not able to get wide enough areas efficiently to find these massive rare galaxies. Euclid can do it, but not at the resolution, and Roman is going to fit right in that missing gap and clean up this multiplicity that we see. As well, HabWorlds will be a groundbreaking facility for studying their massive descendants in spectacular detail, I think, especially with the IFU, which I'm very much looking forward to. So thank you for your time. I know we went a little bit long. Hopefully I touched on some interesting points and made a very strong case as to why Roman by itself is going to be amazing, but when you combine it with Euclid and bridge that European-American gap, we are going to be able to, as an entire global community, accomplish what 100 years of galaxy evolution studies has only been able to hint at. And I think we have an exceptionally exciting decade ahead of us. Thank you very much.
Thank you for the very nice talk. I'm so excited to hear people got excited about the wide area survey after serving on that community for a year.
Yeah,
It's
Aaron,
worth it.
sorry. Can I mention something really quickly?
Yeah, go for it.
Yeah, so I just want to acknowledge that a lot of the work here for myself is, so I am supported by the Brinson Foundation with a Brinson Independent Prize Fellowship. And I just want to give a pitch for this because it's still new, first 3-4 years or so. So the Brinson Foundation provides 3 independent prize fellowships each year. The projects must be related to observational cosmology, but that's a fairly broad definition. First galaxies fall under that, for example. It provides a generous salary and a budget comparable to NASA Hubble. Has tailored career support and symposia, and as 2025 is open to all nationalities. I'm incredibly grateful for the vision of the Brinson Foundation. And if anyone has any questions or is interested in learning more about the fellowship, please get in touch. I'd be happy to talk with you. Thank you.
Is it just one fellow per? I don't know how many fellows do they do every year?
Three per year, but they
Okay,
don't want more than one fellow per year at those institutions, at each of
gotcha.
the institutions.
Yep. Great. All right. Any questions from the room? I mean, you touch on so many exciting things, so I'm sure people have things that they want to talk about. Don't be shy. I can go first. So I saw that you have you did the bravery for extracting these two sources that are overlapping in JWST. If you go back to that star formation history that you extracted, looks like both of them are bursting. And I can't wrap my head around that. You know, if they are in such close proximity, I would imagine whoever started forming star first would, you know, maybe quench star formation in the other one. So I don't know, maybe following up on with some IFU, stepping, resolve star formation map. I don't know.
Yeah, thank you for the question. That's a great question. I'm really looking forward to following up this object with higher resolution IFU.
Yeah.
I did my start in post-starburst galaxies from Manga and VMOS. I see IFU science everywhere. It's addictive. And I'm very glad that for the vision of the NASA definition folks for putting IFU on web. It's been incredible. MSA is great too, but the IFU wouldn't do very much here, unfortunately. This is really an
Yeah.
MSA target. But to the point about the bursting, yeah, I completely agree. I suspect that this is a galaxy that's following the paradigm set down 20, 30 years ago about the AGN merger connection. There's evidence that this galaxy may have emission lines consistent with AGN.
Mm.
See Triber et al. 2025 for compilation there. And I think the bursting is coming from the interaction. And I wouldn't be surprised if this galaxy has already
Mm.
done one passage and that we're seeing a burst happening due to the interaction.
So cool. Merger-induced starburst.
Exactly. And once you look at one merger-induced starburst, everything is suddenly a merger-induced starburst because it's such a easy way to explain things. And I think very compelling and I think probably correct for the most part.
Yeah. Yeah, it looks like the object is a little too small for those micro shutter already.
Yes. And
Yeah.
I think I have a slide later on. I can just take a second to talk about the technical difficulty here if you want.
Yeah. Go for it.
I mentioned that I used the method of Horn et al., which is now a very well-known method for doing this. I'm very grateful that one of my mentors in undergrad was Keith Horn. That's going to play from start. That is now going to play from that. Sorry, one second.
Next.
And so I was taught front and center day one about how to do this. And so here it's sort of looking like what we're doing. So instead of taking a single line spread function, making a cross dispersion width based on the profile and extrapolating it, I take two, which means that instead of solving for one normalization every wavelength, which is vectorized and totally linear, you have to do two for every
Mm.
wavelength, which is not linear. And ideally, you'd want to do this in a Bayesian way. You'd want to tie together neighboring wavelengths, and I just didn't have time to do that. So we just did an extraction propagating the position of the two objects through the shutter onto the detector and then making those models. The lower component sits in sort of the bad corner, which I don't have something to show that here. It sits in the bad corner of the MSA, and so it had a higher slit loss. And so all of this has to be recalibrated once the extraction is done. And so to do that, I went and modeled all the NIRCam data to get the flux anchors to then perform the photometric calibration on each object independently as a function of wavelength by fitting these differential splines between the extracted spectrum and what the photometry says is there. And this is very important redword of 3 microns because formally the objects are blended in NIRSpec redword of 3 microns. And so trying to collaborate the idea of that they're both bursting using optical emission line like H beta is very difficult because H beta is still likely blended. And so they're going to just appear similar in their star formation rates more than they probably actually are. So this was incredibly challenging, but I think really worthwhile. This is showing, for example, some of the differences in the emission line profiles and strengths for the two objects. And it's really cool. We took this philosophy and did it also, as I mentioned, for the IFU data. So here, for example, is the fitting optimization for the three components as a function of time. The top is the input slices, doing every wavelength independently, but with the same, with the same shared model, but independent fluxes. The model's in the middle, and then the bottom's the residual. But of course, I can show this same slice for every single wavelength in the IFU.
This is so cool. How automated this process can be? Because this is, of course, you have put in a lot of work and it seems a lot of manual labor in this one, right?
Yeah, so doing it for MSA is fairly automated, but you do need to have really robust positions as priors.
Right.
I mean, you can try to solve it, but for the cross trace, you tend not to see two Gaussians. You just see kind of one wide hump that you have to trust that two Gaussians fit into. But it does work, and I think this could be powerful. But we got very lucky with the positioning. I just want to underscore how lucky we got with that. And here with the IFU, this is actually very easy to industrialize. You make a detection image, you run classical detection to get the centroids. You then use source extractor segments, sizes, etc., as priors. And then you have to assume some kind of Sirsic profile because usually these things are unresolved. And I was able to, for the 5 targets, I was able to automate this with the same
Yeah.
conditions for all 5.
Yeah. I'm sure there's a lot more to look into once you open the floodgate into the archival data.
Yeah,
Well,
exactly. And we're doing the similar thing for the entire Euclid deep field program. The 50 square
ah,
degrees, we're going to do, 50 million galaxies to blended, including IRAC, all using Sirsic profiles. And I'm very proud to say that for internal Euclid access, we were able to get catalogs put together just this past week after putting a lot of CPU hours in to get this all done.
nice. Great. Well, I've been dominating this chat. So, any other questions from the room? Don't be shy. I mean, I could do this all day, but I'm sure listeners might have something that they find interesting and wanted to discuss as well.
Yeah, and if anyone has any questions from the YouTube audience afterwards, feel free to email me. I'm very happy to discuss things. And I've been presenting a similar talk to as part of the NASA's Universe of Learning, in fact,
Ah,
to a couple astronomy societies, and the questions I got from them were amazing, and I was immensely impressed and surprised at the level of knowledge and understanding of what's going on in the field. So thank you to everyone at NASA and Space Telescope who's involved in outreach. It's working very well. Although these folks are a little more in the know than the average public, but it's incredibly refreshing to see how these discoveries and all this hard work is being appreciated and digested by the public at large.
nice. Great. Well, if there's no other questions from the room, let's thank John again. And thank you all for joining us today. And we'll put this talk on YouTube and we'll see you all back in a month.
Thank you
All
very much.
right. Thank you. Let me